Alright, so matrix multiplication and addition and whatnot. I think everyone's fairly familiar with the matrix. This matrix is a 2 by 3. So this is matrix A. We would say matrix A is 2 by 3. 2 rows, 3 columns. Okay. I don't think that's new or interesting to anybody. I would like you to think of it this. The classic definition is it's a rectangular array of numbers or a rectangular array of elements. Sometimes we refer to the numbers inside of them as elements. I don't really care if you know that or not. It's not a huge deal to me. We would call this position here, we'd call that A. Now we're in the second row, in the second column, that'd be A22. This fellow here would be A23. So we'd say A23 is equal to 1, and so on. Okay, that's how it's done. It's pretty straightforward, easy little process for naming. When it comes to scalar multiplication, if I took 5 times A, that really means is 5, which would be 15, 20, 5, 30, 10, 5. Okay? Scalar multiplication idea, of course, you're just scaling it up or down, either way. As you, I'm sure, are well aware, you need to have the same size dimensions to add matrices. So if I were to add these two guys together, A plus B, and if somebody asks you someday why is that, well, think about it. It'd be like, this would be Joe's lunch order today, and he had 1 fry and 1 drink. And then this would be Joe's tomorrow. You have 2 fries and a drink, for a total of the last 2 days of 3 and 2. And of course this would be for Bob or somebody, and then for Susie. There you go. Okay. Again, not very difficult. Basically, you're adding vectors, because that's really all a matrix is. That's how I prefer to think of it, as a collection of vectors. You could think of it as a collection of 2 column vectors, or a collection of 3 row vectors, whatever makes you happier. Now, typically, when I'm adding, it doesn't make any difference to me whether I think of them as row or column. However, when I go to multiply, I suppose I have this guy here. And I'm going to multiply that one by this guy. Notice that this is a 2 by 4. We're going to multiply by a 4 by 1. The reason that we can do that is because we're going to take this top vector, which is a row vector, times a column vector. And in essence, we're going to be doing 2, in this case, 2 dot products. So it's going to be 6 times 1 plus 2 times 4 plus 7 times 9 plus 3 times 3. That's going to be my top row. My bottom row, 4 times 1. 1 times 4 plus 5 times 9 plus 0 times 3. And when I'm all said and done, I have a 2 by 1 matrix. These have to match. Those outer 2 be our new matrix. It's 6 and 8 is 14, and 63 is 77. And 9 is like 86, I believe, and then that's 8. And 45 is 53, and that'd be your final answer. In other words, this top one is the dot product of the top row in this column. This one is the bottom row in that column. Okay. Of course, if you were to multiply this, which is a 3 by 3, by the way, we notice that this is called a square matrix, because it's same dimensions, row and column, times a 3 by 2. And when I multiply them this time, the middle numbers are the same, so I can multiply. Outside 2 will be my new dimension. Oh, for the love of Pete. Jeez. Yeah, pathetic. So I got one eye in a baseball game, and the guy was thrown out by 100 feet, and there's only 90 feet between the bases. Anyways, I'm sorry, I just got sidetracked there. So, top row times first column, that's that first dot product. Notice that the first column is going to be multiplied by 3 vectors here. So that means my answer in that first column will have 1, 2, 3 entries. And then I'm going to do it again for the second column, and there'll be 3 more entries for the second column. That's why we end up with a 3 by 2 matrix. So 1 plus 2 is 3 plus 12 is 15. 1, 4 is 5, 9. And then 6 and 30 is, no, 6 and 20 is 26. 1 times negative 1 plus 12 is 11. And then negative 1 plus 24 is 23. And then negative 6, 0, 0, negative 6. Done. Okay, piece of cake. I'm going to show you that on the calculator real quick. Yes, I want you to know how to do it by hand. Yes, you will have to do it on the test by hand. However, in practicality, we'll be using calculators frequently in the real world, calculators or some other calculating device to pull this off. So I'm going to start with T89. I think you should have an 89. If you don't, you're kind of missing out, friend. That's my top row. I'm going to do a semicolon. Do a middle row, 5, 8, semicolon, negative 2, comma, negative 3, bracket. And there, second button up on the left, stow. And the name of it is alpha A. Whatever you do, do not store anything as X, Y, Z, or T. It's absolutely ludicrous. Okay, now do it again. Pick something different. For instance, 5, comma, 9, semicolon, negative 2, comma, 3, bracket, stow, matrix B. And if you want to multiply these guys, it's simply alpha A times alpha B. Bob's your uncle. Okay? Piece of cake. Let's see here. Maybe I will open another calculator. If you're using 84, 89, 83, 84, you need to get a better calculator because you're going to be kicking yourself, I promise, later on. If you're trying to do all of the eigenvalues and whatnot by hand later, you're going to be kicking yourself hard. So yeah, I'll let you use the calculator for some of it when we do some application, but otherwise, no. So second, x to the minus 1, that's the second matrix key there. We're going to edit. And my first matrix was the 3 by 2, and I don't remember what it was, so I'm just going to make up some numbers. Those look like good numbers. Cool. So I just arrow them in 8, like this. Enter 6, enter 3, enter 2, enter 1, enter 2, enter, whatever. And then you must hit second quit. So that's second, and then the mode key right next to it, second quit. Second matrix again. Arrow over to edit, come down to here. We want to make this one a 2 by 2. Or whatever. Okay. Second quit. Bless me. Woo! Second matrix. Just hit enter, that's the name, so it's A times B. You don't have to use times on this calculator. And then arrow down to B, boom, done. Okay? That's how you do it. Obviously, there are different matrices, that's why you have different answers there, okay, if you're using this. Again, if you're stuck on a deserted island, all you have is Excel. Excel does matrix multiplication, it just looks weird. So I'll show it to you. It's one of those ones that, certainly can use it. I'm not sure why anyone would, unless, I don't know, like I say, you're trying to do something kind of neat once in a while. You're like, I don't have my calculator with me. So suppose I have this matrix. Oops. Oh, no. Try again, dum-dum. Alright, and then over here, I don't know, 4, 5, 6, 9, whatever. And then 3 by 2, 2 by 2 is going to be a 3 by 2. So I'm just going to go equals mmult. Notice I had to highlight where my answer was going to go. So this 3 by 2, comma, this 2 by 2. And this is important. It's Control Shift Enter. Done. Okay. Again, I don't know. It's neither here nor there to me how you go about doing it. I think, for instance, on the case of a scalar, I think you look like an idiot using a calculator to compute a scalar of a matrix. You're certainly welcome to. I mean, like, check this out. You're just going to go, hey, I want to do 5A, man. All right, bro. There it is. You're done. Bob's your uncle. Okay? Yeah, cool. So, let's do this. So we're doing some of that business. Something else to talk about is what is called a transpose of a matrix. And so the way to do a transpose is very straightforward. If I say A is this, which of course is a 2 by 3, a transpose is this fella. Now check it out. The top row becomes the first column, or in other words, first row, first column, second row, second column. And what do I have now? I have a 3 by 2. Okay. I know you're wondering, can a computer or can a calculator do this for you? In fact, it can. Good question. So if you just go A, and in this calculator you go second, math, matrix is number 4, transpose, done. Okay. So matrix A, and then matrix, and then if you go to math, transpose, done. Okay. Again, different matrices, obviously, but there they are. A transpose. Okay. Here's a question for you. Can A ever equal A transpose? Well, first of all, A would have to be a square matrix, yes? I mean, it would have to be 3 by 3 or 2 by 2 or what have you. Obviously, a 2 by 3 will not equal a 3 by 2. That's ludicrous. So, first of all, if A, oops, I don't know what that says. If A is square, but what would have to happen? I don't know. I feel like if the first row, say 3, 6, 1, for instance, on the top row, if that was going to match over here, I'd have to have this, right? That's cool. And then if then the second row was 1, 4, 1, right? This isn't. You can tell this isn't going to work. Correct? I mean, you can see that if you swap them around, oh, that's not good. What the heck? That's not okay. Okay? And of course 6, 0, 2. These are not equal. That's ludicrous. Is there a way they could be equal? Yes. In fact, so let's think about this for a minute. If this was 316 here, if this was 316 and that was 316, you with me? When they swap places, they would match up. Then this would have to be 1, 4, 1, and 1. And then, of course, what would the bottom row have to be? Why, it'd have to be 6, and then the 1, and then the 2, right? So, in other words, in this situation, the top row, so it has to be square, and the top row is equal to the first column. Oh, I'm going to say first row equals first column. The ith row equals the jth column. Then you should be good to go. In other words, first row equals first column, second row equals second column, and so on and so on and so on. Okay? That's the only way you can have a transpose matrix that comes out all right. Hey, listen, whenever you're dealing with transposes, the thing to remember is, what would happen if I took, someone might want to know, well, what would happen if I took A times A transpose? Does that mean something? Maybe. Let's say what would happen here if you did this. If you did 1, 4, 1 times, and this was A, then what would A transpose look like? Well, it would look like 1, 4, 1. Hey, can we multiply those? Of course you can. You can get 1 squared plus 4 squared plus 1 squared. What would you end up with? In essence, that would be the magnitude of that vector, yes? Or if you prefer, the sum of the squares of that vector, right? So when you're done, if you had A times A transpose, okay, And so we know what's going to go right here in this first column is going to be AII squared, right? A11 squared. It's going to be A12 squared. No, A21 squared, sorry. Okay. So before we do this, let's see if this is true now. Let's do it. So I'm going to have 4 6 1 2 3 4. Okay, so here you know what the answer is going to be. The answer is going to be 16 plus 36 is 52 plus 1 is 53. And then top row, second column is going to be, so what I want to say is there's going to be a sum of squares on the diagonals, you can tell, right? And then here it's just going to be the dot product of those guys and those guys. So just be aware when that happens. It's going to be 8, 18 is 26, 30. And then, by the way, this one here should be the exact same, yes, because you're multiplying them in the same order. So this is the dot product of the off products. On these guys here, it's going to be the sum of the squares of that venue. So it's going to be 4 plus 9 is 13, plus 16 is 29. Okay. So you can kind of see how that's going to play out. It's kind of cool. It's kind of an interesting deal. You're always going to have squares on the diagonals. I almost put that in the wrong spot. The squares are always going to be on the diagonals. 1 1 squared, A 2 2 squared, and then A, well, that's not exactly how I want to write it. The squares will end up on the diagonals. So you have the sum of squares, and it's the way in statistics we write that as sum of squares. You end up with the sum of squares on the diagonal, and then these off ones will just be dot products. We'll take a look at a little bit of an application of that much later on. It has to do with the matrix equation and regression, how regression comes about. We'll look at that quite a bit coming up. It's kind of a fun deal. You can see where regression comes from, and you can see the matrix equation. Anyway, as I say, we'll talk about that a little bit later on when we get into some matrix, some regression stuff, and it's kind of a fun to know how to do that. And you'll see where that comes in. And then in statistics, we talk about the sum of squares. Sum of squares has to do with standard deviation and variance, and so the variance covariance matrix also comes out of that later on. So we'll spend quite a bit of time talking about it. So I just want you to be clear on that. Don't panic today. I don't want to get it too far afield on this deal. Can you raise a matrix to a power? Is that possible? Only if A is a square matrix. That makes sense? A 2 by 2, a 3 by 3, and so forth, and so on and so forth. Okay, that's the only way that it can be done. There's no other way that can be done. 2 by 3 times a 3 by 2. Sorry, senor. No, cannot do. Okay? So then, is there any pattern that you can see happening? Okay? Is there any pattern that you can see happening? And then work it out. So what I'd like to do is do a nice easy one. Start off with, let's don't do 2. I'm tired of 2. Let's do 3. If this were my matrix, alright, then what would this be here if you took 3 times this guy? So there's A to the first. There's A squared. What are you going to get? Well, you're going to get 3 plus, or you get 9 plus 9 is 18, right? And then you're going to get 9 plus 9 is 18. 9 plus 9 is 18. Voila. Okay, that's nice. Right. Well, then what? Can we keep going here? I think so. What would happen if you multiply by 3 and 3 again? Well, so you're going to get 54 plus 54 is 108. Okay, can you see a pattern happening here at all? Okay, well, I don't know. Well, that's weird. I mean, I feel like so. Well, let's see. We went from 3 to 18 to 108. This is times by 6. Hey, that's times by 6. What? If you did it again, you'd get 3 times 3 times 3 times 3. There you go. So that'd be 324 plus 324 is 648. And what do you get when you multiply this guy? You get times 6, you get 648. So in other words, here we're going to have 3 to the 0 power. Yes. Here you're going to have 3 to the, well, how would you write that, I wonder? How would you write that? This would be 3 to the 0. This would be 3 squared, but times 2, I think, yes. And then this guy here would be, or actually I should say it would be 3 to the, so 3 to the 0, so this would be, I'm sorry, it's 3 times 6 to the 0. I was a little off kilter there. There we go. This is 3 times 6 to the 1, 3 times 6 to the 2, 3 times 6 to the 3, and so forth. So in other words, a to the nth power would be equal to 3 times 6 to the n minus 1. No, I have never actually in my entire life utilized that pattern. Do I memorize it? No. Your book started off with 1 where it's 1. I know that it is an exponential relationship. No, I didn't remember that it was that. Where does the 2 come from? Because you're doubling it. You went 54 plus 54. That's where the 2 comes from. But aside from that, no, I'll never use it. But it's kind of a cute little thing, I guess. Like I say, like I always say, you know, you want to impress some folks, you know, someday. Just remember, should they be impressed that you know how to square a matrix the quote easy way? I don't know. That's weird, folks, with it. All right, so I'm going to show you this. This is a way to multiply giant matrices. To be quite honest with you, this probably should have gone out with the dodo bird. I think it's interesting to see it. I think it's kind of a neat deal for that standpoint. But in terms of actual usage, no, I'm not going to do this. Suppose you had a matrix that was 1, 2, 1, 0, 3, 4, 0, 1, 1, 0, negative 1, 1, and 0, no, yeah, 1, 1, negative 1, and then B was 1, 0, 0, 1, and 0, 1, 1, 0, and 0, 0, 0, negative 1, and 0, 0, 1, 0. Alright, now that's a gross mess to multiply out no matter what you do. You're clearly going to get a 4x4 out of that. Okay. But some things that someone might notice, you got 4 zeros right here. What happens when you multiply, let's say, a 2x2 of any numbers times a 2x2 of zeros? You're going to get a bunch of zeros. Okay. So that's kind of neat. So this little piece here kind of stands out in my mind right there. This piece stands out in my mind because this up here on top is the identity matrix. And maybe it's been a while since you've seen the identity matrix, but there it is again. Yeah, so check this out. What we've just done is what was called partitioning matrices. And then you can multiply by partitions. And again, I don't know, it's not going to hurt you to see it, but it's not that exciting either, okay? So what we're going to do is we're going to treat this as, we got A11, that's this matrix right here, yes? And then we've got these sub-matrices, that's 1, 2, and then you got A21 and A22. Alright, and then if we were to multiply that times B, we'd have, of course, B11, which would be this fella up there. B21, B22. And when you multiply them out, of course, you're going to get what? Well, you're going to get A1, 1, B1, 1 plus A1, 2 times B2, 1. That goes in the upper corner. That's this times this. And then for over here, you're going to have A11, B12 times A12, B22, right? Plus, it's plus, stupid. And on the bottom row, you're going to have A21 times B11. So this times that. Plus A22 times B21. And A21 times A2, or idiot. B12 plus A22 times B22. In other words, you're going to end up with another matrix. Now you're like, well, wait, that's a 2 by 2. Not so fast, Haas. This little bit right here is still a 2 by 2. This little bit right here is still a 2 by 2. So that's 4. That's 2 by 2. That's 4 entries, and times 4 is going to be 16 total entries. Now, a couple of things to mention before we do this problem. Maybe it's been a while since you've seen this. 1, 0, 0, 1. This is a 2 by 2 identity matrix. Any on this side, M by 2 matrix times this 2 by 2 identity will give me A again. Okay? Clear? Now, suppose you took this guy here, this A, which is not A, this is identity matrix, and you multiplied it by A, but where A is a 2 by M. Okay, well then again, you will still get A. Okay? And then of course, it could be done for anything. So if you had an N by N, this is how the big kids write the zeros everywhere else. They just write zeros like this, and you'll figure it out. This is an N by N matrix. You see that? Identity. So if I multiplied it by A, I will get A. That is assuming I have an M by N A matrix. Yes? So there it is. Could it be an N by N? Could be an N by N. So that's going to be helpful. And of course, anything times the 0 matrix, doesn't matter what the 0 matrix is, you will just get the 0 matrix back out. Yes? Doesn't matter how big the matrix is, as long as you can multiply it, you're good to go. So when I do that, oops, not there, come back. This fella here then, what I've got, you can see is, well, there's an identity matrix, there's an identity matrix, and there's a big fat 0 matrix. And there's another identity matrix. This guy here is similar to identity, except, it's a little bass-ackwards. If you want to, you can do this. I don't memorize these. Oops. I don't memorize these. It's too hard. The identity, of course, I have memorized. Now, I know what this one does, pretty much. I have to stop and think about it, but I vaguely, it's whatever. It's the opposite identity matrix, yes? So we have this guy, 2, 4, 1, 3. What would happen? Well, 2 times 0 is 2, plus 4 is 4. That would go in the upper column. Now, for the second row, it'd be the top row, second column is going to be a 2, a 0. And you're going to get 1 times 0 is 0, 3 times 1 is 3. What just happened there? I don't know what happened there. And then 1 times 1 is 1, and then 3 times 0 is 3. Oh, look, what happened? There you go. That's it. That's all that happened, man. So I always have to stop and think about what that does. But I normally don't take the time to think about it. I just go, oh yeah, I'm just going to multiply it out. So come back over here with me to this fella here. And I think I'm going to copy that data. See if I can anyways, maybe. Well, that's most of it. Alright, so there it is. Oh no. Oh no. Alright, so let's do this. So to do this, I'm going to treat this as a row in and of itself. But it's going to be this matrix times this matrix plus this matrix times that matrix. Well, that's easy. 1, 2, 3, 4 times the identity matrix is 1, 2, 3, 4. Plus anything times the 0 matrix is the 0 matrix. This becomes the new top entry, you see, in my new matrix. Now let's take top row, far column. Okay, so if I just did this a second ago, it's going to be 2, 4, and 1, 3. I just did that a second ago, so that's no big deal. Plus, here's the identity times anything is the anything. And then bottom row, first column. Identity times identity is, of course, identity. And then anything times the zero matrix is the zero matrix. And then here we go. Identity times this mess is that mess. And then, listen, I don't know what this one is. Well, it's kind of a lie. I do know what it is, but whatever. So here it is. So -1 times 0 is 0. And then 1 times 1 is 1. And then -1 times -1 is 1. 1 times 0 is 0, so there it is. And then you're going to get 1 times 0 plus -1. And then you're going to have 1, -1, and 0. So there it is. So if I've done this correctly now, this and this and this is going to be, well, 1, 2, 3, 4. That's my first top 4 entries. And then identity plus zeros is just this identity. And then this would be 2, 0, 5, 3, 1, 2, 0, -1. That right there is the answer to A times B. Okay. Now, keep in mind that it doesn't have to be broken off into 2 by 2 sections. Again, I'm going to do one more just for a good time. I enjoy this so much. This is my favorite thing on the planet, I feel like. Here's A. Who doesn't enjoy a little matrix multiplication on a Friday night? I mean, come on now. Come on now. Okay, so looking at this, nothing stands out except for like this right there stands out to me. That identity matrix. Do you see it? But if I chop it there, I have to chop the other one this exact same way. But that's kind of cool because then the identity matrix is going to give me, whatever I times it by. That's hot. And then, of course, here it's going to be just a number times a number, so that seems pretty straightforward. And then here's this 0 vector, so that's going to give me some zeros, so that's going to be pretty all right. Keep in mind that once again I have A11, this is A12, A1 or A21, A22, B11, B12, B21, B22. So let's do this. So identity times this fella here is that fella. Right? And then I'm going to have, I'm going to have 1, 2, 3 times 1, 1, 1. Well, when you do that, you're going to get, well, I feel like you're going to get what? Well, you're going to get 1, 2, 3. Oops. Sorry, you're not going to get 1, 2, 3. Hang on, hold that thought just a minute. So be careful when you do this. Just be a little careful. Okay. So it's this row times this column. Okay, which is going to be a 1. Okay. Remember, this needs to be a 3 by 3 matrix, because what I need to do is I need to take and I need to add A11, B11 plus A12 times B21, right? Because I'm taking this row times this column, and it's a little weirding me out, right? And at first you're like, oh, but relax. What does that mean? It simply means I take row times columns. And you're like, what? Yeah. So 1 times 1 is, well, 1. 2 times 1 is, well, 2. Well, wait, I lied to you. Hang on. Back to trans a little bit there. Let me back it up. So top row, first column, 1 times 1 is 1. Top row, second column, 1. Top row, third column, 1. Middle row, third row. Whew! This number is going to give me this upper quadrant, if you like that, in my new matrix. Now, let's do this. So that's the first set. And then I'm going to have A11, A12 times B12, or B12. Oh, you idiot. I'm just going to look funny. A11 times B12 plus A12 times B22. So, let's do that. Identity matrix, which is a 3 by 3 times a 3 by 1 will give me still a 3 by 1. So identity times anything is itself, right? Because the identity matrix is the matrix equivalent, basically, of 1. So when you multiply the identity matrix, this guy here, times 1, 1, 1, you will get 1, 1, 1. And then when you take this guy here, right, times negative 1, you will get what? Well, it's like multiplying by a scalar. You will get this guy. Okay? That's your top row of your new matrix. Oops. So let's see what happens here. Now, we want to do this 0 vector, which is a 1 by 3 times a 3 by 1. 1 by 3, 3 by 1 is going to give me a 1 by 3 when I'm finished, yes? So let's see that. So 0 times, so I have this row times this first column. What are you going to get? Well, 0, 0, 0, 0, 0. That's what you're going to get. And then 0, and then 0, and 0, and 0, and 0. Oops, I'm sorry, no, not 0, 0, 0. Just one row of zeros, you stupid. Remember, write the matrices out. 1 by 3 times a 3 by 3. They match. There's your new measurement. This is the bottom. Plus, now, be careful with this now, because people will screw this up too. So you've got that, and then you can have 4. That's negative 1, I think, isn't it? No, what is that number? No, it's 4. 4 times this guy here. Well, it's going to be just 4, 4, 4, right? And then last but not least, I'm going to have this guy right here. So it's going to be 0 times 1 is 0, 0, 0, 0, 0. But remember, that's just a solid number. It is in essence a dot product. And there you go. So if I've done this correctly, I will have now 2, 3, 4, 2, 3, 6. 3, 3, 4, and then 0, 0, 0, and then 4, 4, 4 is 4, 4, 4. And then 1 minus 1 is a goose egg, 1 minus 2 is negative 1, negative 2, and negative 4. I'm going to check my answer, see how good I did. Oh, wait, that's an even one. Alright, I'm going to check on the calculator. I'll be right back. Well, no, I won't be right back. I'll just type it in. So here's my TI-89. Again, this is why it's kind of a bygone thing to do. I mean, what's the point? I can bust it on this thing faster, and I mean, here's the thing. If you were back in the day doing it fast, I will grant you that you were faster than I can do it now, because it's one of those things that I get it. I could play the game if I had to. No one's going to do it this way. But back in the day, this was a cool shortcut. The only reason I mention it anymore, really, is so that you can kind of see that, so you can kind of see that some of the rules of matrices apply. You can kind of see, you can use them in a way that kind of works or kind of makes you happy, perhaps. I don't know. And maybe you learn a little something along the way. Oops, that's not a semicolon, you moron. Semicolon, there you go. 0, 1, 4, 1. Semicolon 0, 0, 1, 1. Semicolon 1, 1, 1, negative 1, Cross your fingers. Store matrix B. Alpha A times alpha B. Cross your fingers. 2, 3, 4. Whoa, where's my answer? I forgot what my answer is. Come back. 2, 3, 4, 0. 2, 3, 6, -1. 3, 3, 4, -2. 4, 4, 4, -4. Yeah! Yeah, line up, ladies. Let me show you how we do a little linear algebra tonight. Yeah. And you'll be all alone at the end of the bar, friends. I wouldn't recommend it. At least I wouldn't think it would work. I'd never try that because I wouldn't have the guts to try that. Hey, look how weird I am. All right, that's all I got. Bye.